Good morning. Is everyone having fun at the conference so far? So as Rob said, I have been doing things with 30 and 40-year-old computers for the fun of it, so which brings us to today's plenary. We are going to make a simple Commodore 64 game in CppCon today. But before we get started, who all here regularly needs to program for desktop and server systems, ARM, I'm assuming most people, yeah, okay, there we go. PowerPoint just crashed. That's very strange. All right. Yeah, it actually seems my computer just rebooted on me, so just a moment. So I'm going to actually fully reboot my computer now, and without the HDMI cable plugged in, and we'll continue the poll. So the first question was, who all has to program for regular computers? That's everyone, basically, right? Who programs for microcontrollers? So that's I don't know, 10% of people. So does anyone here regularly have to program for 40-year-old 8-bit CPUs by any chance? 8-bit CPUs, but not... Really? What are you programming for? AVR, does AVR not do 16-bit math? 16-bit emulated, okay. So today, while we wait for my computer to reboot, we're going to make this game for the Commodore 64, and we're going to do it in CppCon, and we're going to have fun while doing it. So the point is, what we're doing here today is not going to be 100% applicable, because rarely do people have to program on 40-year-old computers. But it's still going to be fun. And it'll be something that hopefully you can take away from it that you can apply to your normal daily jobs. My computer is almost done rebooting. And so we did that. Going to implement a simple game, CppCon, we're going to have fun. I'm not going to program every single line live. People tell me on my YouTube videos that when I don't speed up all the programming stuff, it gets really boring, so we're not going to do every line live. So we're going to be using Matt Godbolt's Compiler Explorer. Is everyone familiar with gcc.godbolt.org? Yeah. So if you're not already following Matt on Twitter, follow him right now. He has like 989 followers when I looked this morning. Let's just get him over 1,000, and so we can go, hey, the presentation must be going right now. We're going to be using a latest version of Clang from Git so that we get all the CppCon features that we want. And we're going to be using an x86 to 6502 conversion tool. We're not actually compiling directly for the 6502 processor, and I'll fill in the details on that. I personally grew up using the Commodore 64. It was the second computer that my family had, and I didn't really understand what it was doing. I just programmed in BASIC and did some peeks and pokes and stuff, but never really understood the architecture. I decided today I wanted to learn more about the Commodore, but why not use my favorite programming language while doing it? Of course, no modern compilers officially support the 40-year-old CPU in this Commodore. So we're going to use our modern C++ compiler with full optimizations enabled because we want to generate the most simple code possible. And we're also going to be asking the compiler to output 32-bit 386 instructions, again, to keep it as simple as possible. And then we're going to translate this to 6502 code for the Commodore 64. Most people consider this to be absolutely insane. I actually have a comment on my YouTube video that says, this is the stupidest thing I've ever seen. Which seems like a pretty low bar to me. But it turns out this is actually a little bit easier than writing a 6502 backend for LLVM. There's several people before me tried to do it who know more about these things than I do, and they were not successful, so I didn't bother trying. And also, sometimes doing the crazy thing is more fun, assuming it's not when you're at work. So this is what our translation looks like. If you know some assembly language, cool, you can probably follow this. The first line is saying, we're moving the value 10 into the register called AL. And then on the right side is the 6502 version. You cannot directly load values into memory on the 6502. So we're saying load the accumulator with the value 10, then store that into memory location 3. I've done some mapping between x86 registers and 0 page on the Commodore. But if you can read this, cool. If you can't, rule of thumb, less assembly is better than more. This is the Commodore 64. And you know, if you'll just indulge me for just a moment, I am going to start up my VM that I realized was lost when I crashed. So get that booting. All right, this is the Commodore 64. It was released in 1982 for $595, which is about $1,500 in today's economy. It has a 1 megahertz 6510 CPU, so that's for the people who are going to correct me. It is technically a 6510, not the 6502. 6510 adds an extra I/O port that the 6502 does not have. But the technology is from 1975, so it's 41 years old now. It has 64K of RAM, and it's an 8-bit CPU with a 16-bit address space. Now, comparing this to this computer that I saw in a Target ad a couple of months ago, it's the latest version of the Acer Aspire 1 netbook for $150, about a tenth the price. It's at least 5,000 times faster. And that's not taking into account the much higher efficiency of the CPU. And personally, I love the way this worked out. Turns out that 2 gigs of RAM is exactly 32,768 times more than 64K of RAM. And it has a 64-bit CPU. So if you know anything about CPU caches, what we're going to be creating today can easily fit in the level 1 cache of the CPU. Maybe a little bit more realistic comparison is this TI MSP 430 microcontroller. It's $5. It's like $1 if you buy it in bulk. Runs at 16 megahertz, 66K of RAM, 16-bit CPU, really on par with what the Commodore has for its processing. And I mentioned this one because it has some level of official GCC and Clang support, but I don't really know how good that support is. Does anyone know? Anyone? Someone said something. Yeah, well. All right, so I'm going to hop back over to my VM during this break and make sure I can get it set up. This is where I'll be demonstrating my compiler explorer because I needed a custom build of it. All right, that should be good. Okay. Oh, well, all right. So this is our game. We're going to be writing PONG. It has the ball that everyone knows that's bouncing around the playing field. You've got bouncy walls on the top and the bottom. You've got your score in the middle, and you've got paddles on either side. So this is my 30-second computer architecture intro for people who aren't familiar. This is what your computer looks like. You have a CPU. Registers can operate at the same speed as the processor can. They're the fastest way that you can work on anything. They're used for scratch space. A CPU really can't do anything on its own, so it has pins with which it talks to the rest of the world. And I know this is an oversimplification, but over its bus, it talks to things like RAM and other hardware peripherals. So in the case of, say, a PC, and if we want to go back to the classic PC, and the architecture is fundamentally unchanged, your VGA card or CGA card would have been plugged in on the bus, and it would have been accessed as if it were memory on the bus. And in the case of the Commodore 64, this is the VIC-2 graphics processor. And the awesome thing about the Commodore is that you can actually look at the motherboard, and you can see, well, there's the CPU, and there's all the electrical traces that run to the RAM and the VIC-2, and it's all I mean, you can literally trace it out if you want to and see that the RAM and the video processor are attached to the same exact bus that the CPU is attached to. So for the duration of this talk, we're going to be playing an overhead game. I am going to put some code up or propose an idea and ask you if we can do this, if it will take some overhead at runtime or no overhead at runtime. Just binary. And someone suggested to me that I actually have you guys switch sides of the room live, but I don't think that'll work. So with memory mapped devices, as I already alluded to, they're devices that are connected directly to the CPU's address bus, and you read and write to specific memory locations to actually control these devices. So in the case of the Commodore 64 with its VIC-2, if you write to location D020, the value 1, this is equivalent to 53,280 in decimal. And you're telling the video controller you want to set the border color to white. And let's see if everything is working. Okie doke. So this is the latest beta version of the Compiler Explorer. It's not yet live, but Matt helped me out a lot to get this going. What we have on the left is our C++ code, and the middle is the x86 assembly output, and on the right is the 6502 assembly output. And I think I'm breaking one of the main rules of giving a plenary session on having a bunch of assembly on the screen, but I'm going with it anyhow. So you can see like line for line here what it's doing. We're simply setting with a reinterpret cast the memory location 53280 to 1, and on the x86 side, we're moving the value 1 into memory location 53280. This line is resetting the EAX register to 0 because that's where the return value is stored, and then it's returning from main since the default return value for main is 0. And then over here, the Commodore version's the same. We're loading the value 1 into the accumulator, then we're storing the accumulator to 53280, then we're zeroing out what I have configured to be the virtual EAX register, and we're returning from main. Okay, so obviously if we're doing lots of memory access with these memory map devices, and we're having to do a lot of these reinterpret casts, this would start to get ugly. So I want to move this into a function. And so the first question is, can I move this into a function with some overhead? Let's say some overhead first. I get a handful of hands. What can I do it with no overhead? That's most of everyone. And if you have not used the Compiler Explorer, this is an amazing tool for being able to see the code compile live. So we're calling memory 53280, we're setting that equal to 1. Now this appears as though we have added some overhead, but what we have at the top is the function memory itself, which is ending up in the final binary. And we also have on the 6502 side, you've done some stuff that our 6502 translator doesn't understand yet. But really, we don't need this to end up in the final binary because it has been inlined for us. So we're going to put it in an anonymous namespace, which is essentially making the function static. And then the compiler helpfully doesn't put it in the resulting binary for us, so we get a cleaner view of what we're doing. And this code has a problem. Does anyone have any idea what it is, actually? It'd be great. You can yell answers at me. I'll repeat them. You need volatile. Who said that? Way in the back. All the cool kids. All right. So if we wanted to set the background color first to, actually let's do this, to white, then we want to set it to black. Compiler outsmarts us. It says, you set that memory location, then didn't read from it, then you set it again, so I'm going to throw away the first one. And that is not what we want at all. So if we add volatile, then we get what we want, and we set the two values. So now the next thing that I'd like to toy with is putting this in a lambda function so that I have a little helpful wrapper, so it's a little bit more verbose for what I'm doing. Will that take some overhead? I get 1 vote for some overhead. No overhead is everyone else. So border. It's kind of impossible to make a mistake when you're using the live programming here to tell you everything you did wrong along the way. So, border of 2. So that gets compiled away, perfectly inlined. We've got no overhead. But ultimately, for the sake of this demo, what we want to do is build up an object that helps us work with our Vic. And I guess I should have polled before. Who thinks I can do this with no overhead? So adding the object doesn't add anything to it at all. The compiler sees that this object has no member data. It's trivially constructible, trivially destructible. It's not doing anything, but it's a handy place for us to access our Vic registers. So there you have that. And also, we are using some CONSTEXPR and some constants and stuff, and it all just goes away. It's great. For some reason, my normal Windows keyboard shortcuts haven't been working since the reboot. So this leads to video memory. We've discussed the border color, 53280. We've got the background color, which is 53281. And then we have the body of the video memory. And this is configurable, but by default, it is at location 1024. So this is just a flat, linear array of address space to write data to the screen. So if we wanted to write to the 5th column on the 3rd row, we would write to location 85 plus 1024. So we're going to need this capability for displaying the scores on the screen. So building from our last example, and now I don't have the 6502 output displayed anymore, but if anyone has any questions or any concerns about the 6502 is, I do have it set up so that I can switch back and forth between them as soon as it starts compiling. Well, we'll stick on the x86 for most of this because that's most realistic to what we're doing, what you guys are going to be doing in your normal jobs. So again, we're doing 1024 plus 10, which is the column, so we're saying column 10, plus 11 times 40. It's a 40-column display, so we're writing to the 11th row, 10th column, the value A. Now, this is something that I want to move into our vic2 object with some overhead. I'm not getting any hands. No overhead? All right. So the compiler can do some really cool stuff with constant folding and other things that I don't fully understand. If you went to Gore's talk, by the way, yesterday, and he broke down how the compiler optimizes away coroutines, that was really cool. You should watch it if you didn't go to the talk. Right. I actually need a vic2 object to work with. So, as you can see, as you all have guessed by now, no overhead. Compiler is able to do all that at compile time. And I'd say the first time I saw this personally, it was moderately surprising to me. I didn't know that it would do that necessarily with function parameters. I mean, obviously, in the first part, yes, why wouldn't the compiler multiply this out for you? But I think that's cool. And I really wish I knew why my keyboard shortcuts weren't working. Oh well. So it's a game. We're going to need some colors. The VIC2 on the Commodore 64 supports 16 colors. These are approximately the colors that it supports. There's a fair bit of discussion and analysis you can find on the internet about what exactly are the colors that the Commodore can display. It's, so we have value 2 is known as red. It is anywhere not nearly a pure red. It's approximately 136, 57, 50. Then we have light red, which is 184, 105, 98. And these things all have names. There's medium gray and light gray and dark gray and purple and light blue and dark blue. And, but it differed between PEL and NTSC. And apparently there's a huge variation in the resistors that were used in the color generation hardware of the Commodore. So really every single Commodore produced slightly different colors. But what we want for our purposes is to make working with a fixed pellet easier. I don't want to have to memorize or create some table that tells me that 2 is red or something. So my idea is that I want to convert from RGB to the nearest available color on the Commodore 64's pellet. And I'm going to do this by pretending that RGB values represent XY coordinates in 3D space, and I'm going to look for that point in space which is closest to our reference RGB that we are looking for. I want to point out, this is not accurate to how the human eye sees colors. That is a much more complicated process, but we're also only talking about mapping to 16 different colors, so I think it's going to be good. I think I know what's happened. I think, yes, my virtual machine here actually opened on the wrong virtual desktop on Windows, which is why my keyboard shortcuts aren't working. Oh well. So who thinks that I can do this conversion to RGB values, from RGB values to the Commodore's pellet with some overhead? Oh, I'm getting some hands back up again. Who thinks I can do it with no overhead? The majority. So I have this, this code here now. I've created a struct called color. This num is the index in the Commodore's pellet, and we have RGB values. And scrolling down to the bottom, I have created an array of these colors, 0 through 15, and their approximate RGB values. And the ultimate goal that we want is to be able to do something like border equals, and I am using some templates for this, vic dot. So we want to say get red, which we saw in our example is the value 2. Colors. Okay, so I haven't actually implemented nearest color yet, but what I have is a color comparison routine that does our, it looks for the distance. It sees which of the two colors is closest to the reference color. So it's just a less than sorting of the colors relative to the reference color that we want. Then we have our nearest color function. And what we want to do is use the min element standard algorithm over the set of colors. And we need to use our color comparison function. And I need to put a namespace on that. Okay. Now the problem we have remaining is that it's returning a color struct. So I need to actually get the index number out. And there we have the resulting code, which looks a little bit more than some overhead. Everyone agrees, I think. It's only, well, I don't know, 350 instructions plus a table of data. Does anyone have any ideas for how we might be able to get this to use less overhead? Did I hear CONSTEXPR? Can anyone think of a simpler way to get this to have less overhead? What's that? Pre-computed table. Yeah, that could work, but CONSTEXPR would kind of get us there, I think, anyhow. So, is there some best practice about using const anywhere possible? Has anyone ever heard that? So what happens if we make our static array here of color data const? So if you don't currently use const anywhere you can, I bet you will after this talk. This brings us to our daily programming puzzle. I wanted to go ahead and introduce it during my talk. We're not using CONSTEXPR, which is what everyone in the audience said that I should be doing. What we did with const here works because the compiler happened to be able to optimize it. And it's interesting, I'm using Clang with GCC's standard library here. I'm not using libc++. And that was the only combination I found where the compiler and standard library were actually able to fully optimize that away with adding const to it. But you can do it with const expression. And I have solved it, otherwise I wouldn't be giving it up here as a programming puzzle for you guys. So the puzzle is to make the nearest color function fully CONSTEXPR enabled. And in your programming puzzle, you're going to have some static asserts that prove that you made it CONSTEXPR enabled. And if you exceed, there's a following puzzle, to sort the palette by luma at compile time, and then figure out what are the lightest and darkest colors in the palette. Oh, and you have to use C++ 14. It's actually almost trivial to do this in C++17 because of the extra CONSTEXPR support that we're getting in C++17 for standard array. But you don't have that. You have C++14. So we're going to help you appreciate everything that you're going to be gaining with C++17. So what is a game without input? Need a joystick. Commodore 64 has 2 joystick ports. And of course, the joysticks are accessed via the memory map like everything else on the Commodore 64, since the 6502 only has its address bus to talk out of. Helpfully, the designers at Commodore made memory port B be joystick 1 and memory port A be joystick number 2, which, did anyone else grow up using the Commodore 64? Wow, a lot of people. Did you ever notice that almost every game used port 2 for the player if it was a single player game? You ever wonder why? I think this is why, because it was the first space in memory to access. I don't know, maybe not. There's also some interesting interaction between the joystick port and the keyboard scan. So the logic's inverted on our joystick data. So if bit 0 is not set, then we know that up has been pressed. If bit 1 is not set, we know down is pressed, etc. To fire. It works the same for both joysticks. So I have here added to our example. We've still got our vic2 struct. We've added a couple of things. We have a test bit function that's just simply returns true if a bit is set. It's pretty straightforward. I have actually marked that CONSTEXPR. And we have a joystick. And in our joystick, we kind of have to do this inversion logic. So if the port number that I'm doing it based off of the ports, how they're actually labeled on the Commodore. So if you're asking for port number 2, then I'm giving you port letter A. And if you ask for not port number 2, I give you port letter B. And I'm using actually a delegating constructor here, which I thought was kind of a neat way to handle it personally. So on my first constructor, it takes a port data. All port data is a uint 8. And in the second constructor, I'm asking for a port number. It converts it, calls the other constructor. And I set the up, down, left, right, fire. So this is what we have is, and I'm using C++17's if initializer list here, if you haven't seen the syntax yet. So the first line is an initialization, and the second expression is what we're actually testing against. So I'm asking for joystick port number 1, and if the fire button is pressed, then I want to set the background color equal to 1. And as you can see, the compiler has completely, it's completely done away with everything that I typed in, essentially. We're simply saying, is the 5th bit of the memory location 53621 set? If it is, then we want to jump up here, move the value 1 into memory location 53281, and if not, then we jump into the loop and test again. So it's handled all of the delegating constructor. It's completely eliminated our entire data structure, even though it actually does contain data now. Actually, it's eliminated 2 data structures for us, because our temporary port data and our bools that are in here. And the compiler continues to outsmart us along the way. If we wanted to say, if up and fire are pressed at the same time, now it has merged those into one operation, and it's saying, are bits 5 and bit 0 set? Then it continues on. And you can continue to add things to it. And it doesn't get much more complicated than that. And has everyone seen the if initializer list? Anyone? Few? Some? Half? Okay. So may as well go into that just a second. With the if initializer list, the value that is initialized in the if statement is available in the else block also. So I could say else if down is pressed. And the compiler continues to compile all this away. So we're using our if initializer list and our objects without any overhead. Is everyone familiar with RAI? I would hope so. Okay. Resource acquisition is initialization. Essentially, we're using constructors and destructors to manage the state and resources of our program. A lot of people consider this to be the greatest strength of C++, but I would like you to consider thinking about it differently. Well-defined object lifetime is C++'s greatest strength. C++ is not the only language with constructors and destructors, but it is one of very few languages where you know exactly when those things are going to be called. So who thinks that we can put some RAII to use with some overhead, two, and with no overhead? Okay, let's see what we got. So what I want to do is so a little bit of background first. Sorry. This code, if you haven't noticed, is really, really tight. We're talking 2 instructions, essentially, right? Or a couple of jumps. So it can operate many times faster than the screen is updating. So what we can actually see in this code is the background color changing several times per raster line as the computer is drawing the rows on the screen. And you would end up with one color that's taking up, like 10 pixels, and then another 10, another 10, another 10. So what we need to do is put some sort of guard in here to prevent us from updating but once a frame. And I'm going to do that by checking to see if we are on the 240th raster line. And if we are, we know we're outside of the normal background drawing area. So a simple busy loop, we wait until we get to the 240th line. Once we have, we continue on, and we're willing to update the background color. And that is here. -16 is 2's complement, 8-bit math for 240. Now we, just for the fun of it, want to increment the border color on every loop. Is that? On every loop iteration, whether or not the joystick fire button is being pressed. So this seems to me like a logical place to use RAII. We want something that will guard us and block us until we have actually reached the 240th raster line, and then we want to do something on destruction on the border. So I'm going to create a new function called frame on my vic2 object. And in here, I'm going to create an inner struct that has our constructor and a destructor. And it needs to keep a reference to its parent vic2 object, because to operate on the border, it needs to have the vic2 object to do that. And compiler is now complaining at us because we have an uninitialized reference in our object. No big deal. And then we'll use our initializer list. And then we return a frame object that takes a reference to the parent object. And now we're going to move into our constructor. And destructor. So to make this work, and we get the exact same code that we started with. So we are effectively using RAII with some move operations. There's no copies of our frame object being created. It just does what we want it to do. I don't know if I'm relying on a not yet guaranteed by the standard optimization for return value optimization. Does anyone answer that? But I can by enabling move constructors. So just for clarity, by putting this destructor in here, the compiler is not creating for us our move operations. By putting in your own destructor, you've disabled them implicitly. So if I wanted to be fully correct, follow the rule of 0 here, which I highly recommend, then we would need to do some move constructor defaults and stuff to make sure they're not disabled. But anyhow, so this is what we wanted. So at this point, I said to myself, hey, maybe I've gone off the reservation. I need to make sure that this actually still doesn't have any overhead compared to writing all of this code by hand. And do we want to take any guesses as to whether or not this will look the same? Let's see. Do we, at this point, have no overhead still? Most people say we still have no overhead. So I have my RAII sanity check, where it is just a bunch of reinterpret casts and calls to memory locations for the joystick port and the incrementing of the background and border color. So this looks different. And does anyone know why? Yes. We still have a volatile problem. And it's interesting that it was like 2 weeks into preparing this talk that I realized technically I was doing my reinterpret casts wrong this entire time. The compiler checks the memory location 53266 exactly once. And if it is not equal to 240, it jumps down to this infinite busy loop. So we need to add volatile. Here, we can add it. And now we have proven to ourselves we still have no overhead. Oh my. There we go. Game needs sprites. Everyone familiar with what a sprite is? Little movable object on the screen, basically. Let's call it that. Commodore 64, or the VIC-2, supports 8 hardware sprites. These hardware sprites have hardware sprite collision detection, which is pixel level, I believe, which is pretty cool. So if 2 things hit each other, then the hardware can notify you that you've had a collision. And the sprites are 24 by 21 pixels each. So I'm going to point out that technically it has 8 hardware sprites per scan line. People will do lots of tricks of updating the sprites as the display is being drawn, because as I already pointed out, we can actually do things in the middle of the frame easily. So if you ever play a game on an old computer and it has more than whatever it technically says it can support for sprites, it's because they're updating the locations during the middle of the screen draw. Sprites can be single color or multicolor, and they can have their height or width doubled. And that's something we'll be taking advantage of, but I'm not going to go into a lot of details. Monochrome sprites. Each bit represents 1 pixel. We have a smiley face. If we take a stripe out of the middle of where the eyes are and assign bit patterns to this is literally a bitmap. And convert that to decimal, we have the values that we need to write to memory to create our sprite for the Commodore 64. So if we do this for the entire thing, this is what we end up with. This is the array of data on the right that we need to write in. Now, what I wanted to do is have the have the compiler actually compile my sprite data for me. So I've written this. This is our bouncy ball. It is the bitmap in the source code, and I am passing this to our makeSprite function. The makeSprite function is a variadic template that is writing all of the pixel data to the specific location we want it to go to. And then this is our write pixel implementation that I need to actually write now. So at memory location loc, we want to assign the value and you guys get to watch me type for a minute. Every time I've practiced the tests, I get confused at D4 equals, D4 shifted left 4 times, because I can't remember which number is going up and which number is going down. Okay. We are writing the very first byte of our sprite data to the specific memory location we want it to go to, which is 12288. And that's a detail of the default configuration of where the sprite data is stored on the Commodore. Not worth going into, but we're sticking with the defaults for this stuff. Now, we need to actually write the rest of the sprite data. And to do that, we're going to call writePixel recursively for the next memory location and the rest of the sprite data. Big compiler error. Anyone know why? Well, I'm missing the 0th case. So once we run out of data, it's expecting to call a function that has no. There we go. So this takes a second to compile. There we have it. We have had the compiler compile for us our sprite resources. And it is writing into memory all the specific data that we want. And I know there are many different ways to do this. In fact, it would be possible to have it create a table and then do a loop that moves the data into the appropriate memory space, but that's not what I wanted to do for this example. So we're actually asking the compiler to do a lot of work. And is anyone, sorry about the switching back and forth. Should be able to get that. Anyone aware of how many function parameters and how many function calls we just made? Does anyone want to throw any guesses out? It's a big room to do this with, but I'm going to do it anyhow. I'll give you a hint. Remember that that was 24 by 21 pixels. What's that? 20. No, more than that. 504 plus 1, because you're forgetting the memory location. 504 parameters being passed to the first function, and how many recursive function calls are we making? 63. plus 1 because of the 0th case. So we just asked the compiler at compile time to optimize away 64 deep recursive function call with 505 parameters to it. Well, I think we should give a hand to the compiler developers. So multicolor sprites, what's the world fun without some color? Now we have a color version of our smiley face. If you notice, the pixels are double wide now. What we have is each 2 bits represents 1 color and represents 2 pixels. So essentially you have each pixel is double wide. Does that make sense? If we keep moving forward, these are the color values for each of these. And then if we split that into binary, we have our 3 octets like we did with the monochrome. And that gives us the values that we want. And we do the same process again. So this is our final data. See if I can start getting smarter about switching back and forth. So I've already stubbed in all of our multicolor sprite stuff. This is the paddle that we'll be using. It is long and skinny because the pixels are double wide. So when this is expanded out by the computer, it's going to be square, but then I'm using the hardware capabilities of doubling the height of it. So that actually gives me square pixels because the pixels were already scaled vertically. Now I'm going, or horizontally, and now I'm going to scale them vertically, but you'll see that in the demo. So we are not compiling at the moment because we have a minor problem. The multicolor pixels have less data than the monochrome pixels. So we need some way to choose between these 2 things at compile time. And we could do this with lots of fun like Sphinx things, or we could do it by simply having a different function call from the beginning. So instead of make sprite, I had make color sprite. But instead, I decided to take advantage of C++17's if CONSTEXPR. So I can do a compile time switch with if CONSTEXPR, and the compiler chooses the correct version at compile time. The version that doesn't need to get called just goes away. Everything works great. So now we have full support for color or monochrome sprite data being compiled at compile time by the compiler. Okay, time to bring this together. But a quick note. The Commodore 64 screen is 200 pixels tall and 320 pixels wide. The Commodore is an 8-bit CPU, so it can only go to 255. Now, obviously, the Commodore hardware has ways of dealing with this, but for the sake of this demo, I wanted to stick to 8-bit math. So the playing field, I've limited it to 255 pixels wide. So this is our final game now. We have our memory functions, our color data, test bit. We have our joystick stuff that we've been talking about, and a key part of the joystick that I kept forgetting to mention when we were actually talking about the joystick, but I've created this function called a direction vector. And it returns an XY pair for what direction the joystick is being pressed in. So the first value is -1 if it's left, 1 if it's right, up and down. So we're using a standard pair for that. And then I've created a couple handy functions for myself that let me do pairwise addition and pairwise multiplication of our pairs. And I've added a new function called setBit. This is necessary for things like setting up the registers for the sprite data. We have our player object. It has an update position member where it is using the direction vector data from the joystick to move the paddle up or down, moving it 3 pixels at a time. We've got, We've got a score. It keeps track of its own score, which we are storing for the sake of this in an ASCII, so I can just write the actual character code to the screen. And we've got a pair of volatile uint8 references that are the position of the current player's paddle on the screen. Our vic2 object is now fully fleshed out with our border, background, display, color comparison, nearest color, our frame object that we were just discussing, but now the frame actually, it has references to the 2 players, and it uses those references to get the score data, displays that, and our sprite data. Then our enable sprite now has been fully fleshed out, and we have this new function called sprite collisions, and I am returning a tuple of all of the collision bits. So if there's been a collision involving sprite 0, then the first bit is set, etc. Sprite colors, okay. So this brings us, so at the moment I have the sprite data and all the boilerplate stuff commented out because I don't want it to get in the way of our looking at the assembly. So this is what our game logic becomes. We have the ball velocity, which starts out as being x1, y1, so it's moving in the up-right direction. We have a lambda, reset ball. This is called every time someone scores, we need to reset the ball back to the middle of the screen. We have our players, and where they are set, what sprites they are using, and where the paddle is on the screen. And here we are using C++17's destructuring capability to get out all of the sprite collision data from our sprite collision function. And we're just testing to see, was sprite 0, which is the ball, involved in a collision with sprite 1 or sprite 2, which are the 2 paddles. If it was, then we want to invert the velocity, x velocity of the ball. So if it was moving left, now it's moving right. If it was moving right, now it's moving left. And then we need to bounce the ball out of the collision area. Otherwise, it has the tendency to get stuck inside the paddle and do this thing. It's not what you want. And so we can see over here, all of this, the sprite collision logic, we had a tuple in there, and we have our destructuring, and then we do our comparisons here. The compiler is doing lots of smart things and simplifying this into a pretty simple read from the sprite collision data, and then a couple of comparisons to figure out where the interactions were. Then we update the paddle positions based on what the user is pressing on the joystick. And now here, this is the end of it. We've got our ball X and ball Y, its current location. So if the ball has gone up to the top of the screen, which is row 45, then we need to bounce it back down, or if it's gone to the bottom, we need to bounce it back up. So we are using those overloads for times equals on std pair that I showed a minute ago to, again, invert the y velocity of the ball. And this logic gets compiled down to very little also. And if the ball has gone all the way to the left side of the screen, then player 2 has scored because it's gone off the left side of the playing field. If it's gone all the way to the right side of the screen, then player 1 has scored, and we update the score. So the entire game compiles, not including the boilerplate, to 83 instructions. So I don't know really what this would be equivalent on a PC if you could do this, but I'm guessing somewhere in the billion frames per second ballpark, maybe. Well, except for the fact that we're intentionally limiting it to one update per frame, which we have to do on the Commodore, by the way. The game's completely unplayable if we don't limit it to one update per frame. So if we uncomment our boilerplate, we'll now see all of the sprite data being compiled for us at the top of the output, and then the rest of the program logic. It's compiling 2 sprite resources this time, so that's 1.5 times the amount of work that we were talking about before. But you can see straightforward sprite 1, sprite 2. Oh, I didn't mention this explicitly, but the 2 paddles are sharing the same sprite data, but the Commodore can have different colors configured for the paddles, so we are giving them different colors. So the entire game is 231 instructions on x86, and on the 6502, it's a little bit bigger. That's because I am doing an imperfect translation. It's somewhere in the 410 instructions, 420. There we go, 419 instructions. And what this means is the entire game, including sprite resources, compiles to 1005 bytes, basically. So does anyone want to actually see the game played, by the way? All right. We're going to attempt to do that with my Commodore 64 that I brought to the presentation. Now, unfortunately, we did have some technical difficulties while setting up, and it would seem that I may have sustained a little bit of hardware damage in transit. So we'll see what can happen. I am going to need a volunteer on stage. I know I talked to Herb. If he's here, you can come up. Let's see if we can get this going.
That's an Atari joystick.
It is. That is an official, original Atari 2600 joystick.
I
Now,
grew up with these.
I also grew up with them. This is why I actually bought these on eBay just for this, because this was the joystick I played all of my Commodore games with. So here's hoping our video is going to work, at which point I'm going to need camera on stage. All right, minor technical difficulties, but we do have a display up here. So as soon as it gets up there, so you'll be the player on the right. I set this up intentionally. Hopefully we can actually see the screen.
I have not seen this before.
No, you have not. This is, if anyone's curious, I actually got it onto the Commodore 64 by using this thing called the SD2 IEC, which is a teeny tiny little 1541 disk drive that uses an SD card, and it actually plugs into the original interface that the Commodore expected. It's amazing that these things are still being developed. People love this hardware. The video cable that I'm using, hey, we're on screen. The video cable I'm using is today manufactured, like it's brand new from a manufacturer in the UK who's making S-video output for the Commodore 64. Oh. We're going to load the directory from the SD card. It's really hard since I can't really actually see the screen. Okay. And what we have is pong.2.cpp.prg. Little verbose, but it works. Now, if anyone's curious, the assembler and tools that I used actually load the game into memory location 4096. So I've loaded the game, but to actually get it to run, I need to jump to that memory location. And there we have, can you see the screen, Herb? It's a little slow. It needs to actually, at some point, speed up, but there we have it. I hope the theme that I went for is not completely lost on the screen here. Well, there is no end to this game, so whenever we get bored. Yeah, and we still have a little. Oh, stuck in the paddle. Oh, there's actually a little. If anyone didn't notice, I didn't put any limits on where the paddle can go, so you can get a little bit of a cheater scroll around there. All right. Thank you, Herb. Excuse me. That's good. I'm glad that worked. All right, why did what we did work? We used straightforward logic in our code. This is the simpler code that you can write in C++, the better the compiler can work with it, basically. So we have very little branching, and in some cases, which I didn't dig into maybe as much as I could have, we actually had branching that the compiler got rid of. We had branching saying, if these states are true on the joystick, and the compiler said, no, I don't need to do any branching here. I'm going to take these values and do a couple of bit shifts, and I'm going to load them into some other registers, and then just do the right thing. And it can do that. So we let the compiler work for us. We've got function inlining was huge. If you didn't notice, there were no function calls, even though we had lots of function calls. Is anyone paying enough attention to notice how much RAM we actually used if you don't include the sprite data? Yeah, 0 bytes of RAM. The compiler actually was able to map every single variable, every single thing we did directly to register allocation. And this is on a 386, 386 compiler output that I'm asking for, which is, I don't know, I don't remember. It has like 16 registers or something. Compared to a current Intel architecture, does anyone know how many registers a current Intel has? Anyone? I don't, actually. I haven't managed to count that high yet. It's in the like hundreds or something. And it doesn't even matter, because if you're writing to registers, and you can talk to hardware people that know more about this than I do, the CPU is going to assign those to virtual registers internally and rearrange everything for you anyhow. So if you keep everything simple, you pretty much don't need to access RAM in some cases. And we've heard some mention at the conference already, the principle of zero-head abstractions, zero overhead abstractions in C++. So today, we used objects with how much overhead? 0. Methods, 0. Delegating constructors and destructors, 0. Lambdas with and without captures, 0 overhead. Structured bindings from C++ 17 with no overhead. Function calls with no overhead. C++ new 17 if and it expressions with 0 overhead. And variadic recursive templates with 0 runtime overhead. And even standard algorithms with 0 runtime overhead. So that brings me to the conclusion. As Rob mentioned, we host CppCast, check it out, and my C++ Weekly YouTube channel, which is how I ended up on this stage. URL, and I've done a couple of videos with O'Reilly if you want to check them out. So if there's questions, ask questions. We've already got one.
Yeah, hi. Even though it's not in the standard, I've noticed that compilers sometimes can deduce CONSTEXPR from const. I was just wondering if that's what happened to your array.
I'm sorry, if what happened to it?
Sometimes compilers can deduce CONSTEXPR from const when you write just const.
Can the compiler deduce CONSTEXPR from const? I would say no, I don't believe that's technically what happened.
I've seen that happen before.
Yes. And there are rules that say, in certain cases, constructors are implicitly constexpr. In some cases, I forget the details. But I think it's just a compiler being really smart there. Because that version of standard array from the standard library I was using does not have any constexpr, or it has very few constexpr methods on it. Yes?
Oh, hey, Jason, great talk.
Thanks.
You have the recursive template formulation. Are you familiar with the for each n args variant pack expansion style that Vittorio's talk covered? Did you try that one?
No, I didn't try it. I've seen some of that stuff. I was aiming for something that I knew I could that the result would easily translate into what I wanted on the 6502. But I also wanted to do it all without having to include any boilerplate code, which I believe I would have to in that case. The for each args.
Well, my curiosity is just, would it optimize away?
Oh, I don't know.
It frequently compiles faster, I think, than all that recursive stuff.
Oh, there's Vittorio. Okay, so he said the for each args after optimization level 1 on Clang and 2 on GCC goes away. Other way around. So yes, it can also go away with probably faster compile time.
Awesome talk, thank you.
Thank you.
I was wondering if you compiled this without exception support, if you handled that anyway?
I didn't need to bother to try. I'm not using any exceptions. I'm not calling any functions that could throw exceptions. There was no exception code generated, it didn't matter.
Awesome.
Hi, thank you for showing the assembly on the screen. It was very entertaining. I had a question. The tricks that you showed, they work one time when you're just doing things like that. But in real production code, you want to make sure that these things continue to be optimized away as the code gets improved. Do you have any tricks to do static asserts or code size or anything like that to make sure that the zero overhead abstractions continue to be zero overhead?
I think probably the most important thing is, in my experience, and I'm sure we would get a huge range of answers from the audience, is avoiding dynamic allocations. By doing as much stuff as you can on the stack as possible, the compiler is able to do some really amazing things with what it's able to deduce from the code. And then I would suggest actually taking advantage of CONSTEXPR as much as possible, and then letting the compiler do its job. Okay, another question.
Just last one. Please, in non-generic code, can we get rid of standard pair and use a struct with named members? C++ 11, 14, 17 tells us that has zero overhead of a standard pair.
Yeah.
So instead of using first and second and custom dangerous overloads on the operators for a generic standard pair.
With generic standard, if I understand your question correctly, I mean, you can use destructuring of the pairs, and you can get away from some of the nonsense of using first and second and keep the code clean.
Yeah.
Okay. Yes.
The amount of code that the compiler generated after the optimizations was simply stunningly small.
Yes.
So do you have any idea what a hand-rolled, say, version of PONG that was contemporary with the hardware might have consumed in memory?
You know, I do not know, but I am assuming that after this video is released on YouTube, I will find out. Yes.
Don't worry, it's good. So you said that this consumes 0 runtime memory. I think that's not accurate. I think it's better than that.
Better than 0.
Because you are using some runtime memory. You're storing the current color, you're storing the sprite at runtime, but what you're doing is you're taking advantage of the memory that the hardware is already using anyway, and you're using it directly without adding any overhead of your own. So you are using memory that's already there and using it the most efficient way possible, which I think is really cool.
That's an interesting point. Thank you.
Just a quick question. How much work was it actually writing the conversion tool from the x86 to the 6502 kind of assembly compared to actually writing the game?
It's probably about 3 times more work than actually writing the game, but I spent a lot of time tweaking the code to try to get what I thought would be the cleanest representation of the game main loop possible. But the 6502 assembler, or reassembler, I call it a reassembler. Actually, I got that name from my cousin. It took, I'd say about maybe a week's worth of work, but the bulk of that work was done in the, before the C++ Weekly YouTube video that led up to where we are today. And it's up on GitHub. I didn't put a link to it in here. But if you look for x86 to 6502, you can find it, and it's pretty good at this point, I would say. So one of the comments on my original video, I got a comment that said this is the stupidest thing I've ever seen. And the follow-on was, it could never work for non-trivial code. And I admit that this is crazy, but it can work for non-trivial code, and it was really fun to do.
How did you go about developing this sort of example? Was it something you wrote all at once? Did you write it in chunks? I mean, the way you kind of walked us through looked very interesting, but is that the way you actually made it?
I have to think about that for a second. I knew what my goal was, and that it was to put a 2-player game on the screen live on the Commodore 64. And I initially thought I was going to have to go with something much more simple than PONG even, and PONG's pretty darn simple. The original PONG is implemented in solid-state hardware. There's no programming involved, but it's also all in black and white. So I kind of proved to myself that I could make the game I wanted to make for this demo, and then I took where I had started on the YouTube video, and I kind of worked towards the middle to get what I wanted.
Oh, and how much time do you think this took you to make? Sort of like in terms of development, was it a week on and off or several weeks of toying around with it till you had what you wanted?
The entire presentation or just the game?
The game.
The game, probably a week and a half. Maybe full-time effort.
I've noticed that you sprinkled, as you said, const all over the place, but I've noticed also a static keyword. Can you talk about static and what was the significance of that?
Oh, the static keyword, so let's see. Let's see if I can get there. That was in, this is the most basic example. Oh, but that doesn't have the palette actually implemented yet. Let's see, because as we just said, this code was kind of generated in stages. So it's possible the static's not necessary there, but I think it actually is for the compiler to optimize it. Oh no, actually in that version, it's not static. So yeah, the compiler did the right thing. Const was the important part. Static started from when I was trying to figure out the best way to organize the code to make it as readable as possible on the screen, and I had moved it outside of the function.
Okay, thanks.
right, I guess that's it. Thank you.